So in this video we're going to continue our discussion of circuits that have any kind of element we want, capacitors, inductors, and resistors. In the previous video we found the solution of the circuit when the source was a complex exponential. Well, that's a mathematical toy. We can't really produce sources that look like that in the lab or in the real world. So is that just a mathematical thing that's kind of fun to play with? Well, it turns out it's much more important than that. We're going to see how to apply that knowledge we developed last time when the source is a sinusoid. Turns out it's an easy extension of what we already have done. So let's review very quickly the way the so-called impedance method works. We start with our circuit. We pretend the source is a complex exponential, and that means we can now only worry about complex amplitudes. We replace every element by its appropriate impedance, whatever it may be, and then we can use what we learned from resistive circuits, voltage divider, current divider, series parallel relations, to figure out how the output variable's complex amplitude is related to the complex amplitude of the source. Okay, so that's what we learned last time, except now we want to handle a bit more real-world sources than complex exponentials. So what we did is we applied it to our simple RC circuit. We replaced it by, thought about it as an impedance kind of circuit. And I want to make sure we note that this is a lowercase v in over here. It's supposed to be v in of t. This is lowercase v out of t. But over here we're only talking about the complex amplitude. So I'm thinking about this as being a complex exponential source. And now everything in this circuit is a complex amplitude. And what we discovered when we used our voltage divider for this circuit was that the amplitude of the source, amplitude of the output rather, was equal to this quantity times the amplitude of the input, and I'm uncanceling the complex exponential so we get the entire answer. Okay, so that's what happens when the source is a complex exponential. Well, what I want to now do is talk about the case where the source is a sinusoid. This sinusoid has a frequency f0, and it has an amplitude of a. Okay, well, that's not the same as a complex exponential. So how does this result apply to the case where that's what the source really is? Well, the mathematical trick is Euler's formula. We know from Euler's formula that a cosine is equal to 1/2 times e to the j theta plus e to the minus j theta. A complex exponential rather at an angle of theta, and a complex exponential at an angle of minus theta. That's a cosine. So that applies to the case where we have theta here is just cosine 2 pi f naught t. So I think of this as being a positive frequency complex exponential, and this being a negative frequency complex exponential. This may sound a little strange, negative frequency things, but it turns out this is really very important and the right way to think about it. So we can figure out what the output is for each piece at least. We know that if the source was this term, that's the output. And we know that if it's the negative frequency term, all we have to do is replace f by minus f, and we get the answer. So we know about each piece of the original cosine. We know what the output is for each of those. But how about putting them together? How do we do that? Well, now we get to the really interesting conclusion. Now, so this is where we are. We use the complex exponential source to hop over to the impedance version, use all the tricks we've learned for resistive circuits, and now when the source is a cosine, I want to point out that all the circuit elements we've been talking about, resistors, capacitors, inductors, and the interconnection laws, KVL and KCL, are linear, which means superposition applies. Remember what the definition of linear was. That if the input consists of a sum of terms, the output also consists of the sum of the outputs to each term considered separately, and you just add them up and multiply by a constant if there are any output. So, we're done. Based on what we already know, we know that the output voltage, and notice this is lowercase v, is the output to the first term plus the output to the second term, added up, and since there's a weighting factor of 1/2, it goes there too. And this is because of superposition, because the circuit elements we've been talking about are linear. This is why the linear concept is so important. It really makes our life easy. Okay, so let's continue this. I'm going to show you how to simplify that answer. It looks a little daunting as it stands right now, but there's another mathematical thing we can do. Now, so this is Euler's formula for the cosine. And the source was 2 pi f naught t. And like I said, I thought about this as a positive frequency term and a negative frequency term. Well, there's another way of thinking about this. Suppose this is a complex number z. This is z conjugate. I'm adding them up and dividing by 2. Well, that's the formula for the real part. And so we're actually writing the source as the real part of a complex exponential. Well, the output looks very similar, right? There's the positive frequency term, there's the negative frequency term, but that still is something plus its complex conjugate divided by 2. That's the real part. So this, if you will, is the trick. We can think about when we have a source that is a sinusoid, you can think about it as the real part of a complex exponential. The output is going to be the real part of the same complex exponential with the amplitude modified by what the circuit does that we found using voltage divider. Well, how do you find this real part? Well, mathematically, we have a situation where we have something in Cartesian form and something in polar form. And we need to figure out how that real part, the easiest possible way. And their answer is to convert the Cartesian form to polar form. So that's what I've done. So this is the ratio of something in Cartesian coordinates, 1 and the denominator, j2 pi f naught rc plus 1. And as I showed you, the magnitude of a ratio is the ratio of the magnitudes. So 1 obviously has a magnitude of 1, and the magnitude at the bottom is the imaginary part squared plus the real part squared, and you take the square root of the result. Okay, that's where that comes from. The angle of a ratio is the angle of the numerator minus the angle of the denominator. And the angle of 1 is 0, and so what we're left with is that's the angle. Okay, so now we need to simplify further. All I'm going to do is merge the two complex exponential terms into one term because the exponents add. And now taking the real part is easy because this is just some real number so far as the mathematics is concerned. The only thing complex is this, and that's e to the j theta. And what's the real part of e to the j theta? That's just a cosine. So our answer is, when the source was a cosine 2 pi f naught t, the output is also a sine wave of the same frequency, but with a different phase and a different amplitude. Very nice. And it turns out that result is quite general. So let's review again how we found it. It's so important, I really want to make sure we get this down. So the source was a sinusoid. I thought about it as the real part. I know by converting to impedances that this is the way the amplitude of the output is related to the amplitude of the source. And over here, that is Vn, right? Because that's the amplitude of that complex exponential. We now know that the output can be written as the real part, where you put in how the circuit transformed the voltage amplitudes, and just finding the real part, just like using the procedure we did, converting to polar form gives us our final answer. Looks a little complicated, but we'll understand what this means in just a second. We'll have a clearer interpretation of it. Now, let's handle a little bit more general case. Suppose there was a phase. The source had a phase. Well, the way that works out is now Vn is a e to the j theta. So it really is a complex number now. Using impedances, we're always going to find that the complex amplitude of the output is equal to something, whatever the circuit does, times the complex amplitude of the source. This something it does is called a transfer function. And if you look back over what we've done, it always depends on frequency. So that's why I had to put the frequency of the source, f naught. And I'm just going to define that to be V out over Vn. In general, it's the ratio of the complex amplitude of the output divided by the complex amplitude of the source. This captures, the transfer function captures what the circuit does to the amplitude and what it does to the phase. So here's what's going on. We found using impedances that that's the transfer function in Cartesian form, and as we've seen, it's much easier to deal with mathematically if we convert that to polar form. This is routinely what we do for any circuit. We use the impedances, we're going to wind up with a result in Cartesian form. We then have to do some calculations to figure out what it is in polar form, and then it gets very easy to figure out what the output is. So when the input is that, the output is always this for any circuit containing resistors, capacitors, and inductors. That's always the answer. This is very, very general. So we now can see that assuming the source was a complex exponential actually had a big payoff because the circuit was linear. Now, I'm going to point out some mathematical details that are very important, and that is, suppose we had a sine wave, real sine. Okay. Well, the easiest way to think about sine is as the imaginary part of something. Well, everything goes through. The superposition still goes through because of Euler's formula, and you also use imaginary part. And this is very important. So however you define the source as being related to a complex exponential, either by an imaginary part or a real part, you use the same representation for the output. So when the input is that, the output is this. And that's, again, a general result. You can use either the real part or imaginary part, whichever one is easier. I'm going to point out that you can actually work this the hard way, if you will. You can assume a cosine is the imaginary part of something. Notice the presence of this because of the phase shift by pi over 2. Represent the sine as the real part of something if you want to. You should actually go back over our little example, RC circuit example, once you try using the imaginary part, and see if you get the same answer we got using the real part. except you have to change the amplitude of the source by e to the j power 2. You better get the same answer once you simplify things, and trust me, you will. Okay, so here's the big picture. For any circuit we have, pretend the circuit is a complex exponential, although it really isn't. Use impedances to find the transfer function. Now we express the source as the real part or imaginary part of a complex exponential. This works for sinusoidal sources. And the output is going to be the real part or the imaginary part, whichever one we assumed. We're going to try to switch them. Of the transfer function times the complex exponential of the source. That's the procedure using impedances to solve any circuit that has a sinusoidal source. So let's go through this for an example. We ought to try something a bit more interesting than an RC circuit. And what I'm showing you here is what's known as an RLC circuit. So our circuit now has a capacitor, a resistor, and an inductor. The source is this, and I'm going to ask you two questions. I want to find the transfer function. I want to find the output for this input. Okay, so we now know what to do. So here we go. So the first thing we do is we take our circuit and replace it by one having impedances, where again these are complex amplitudes. Now, I've done a little notational thing for you here. The impedance of this 1 farad capacitor is 1 over j 2 pi f. Well, to simplify the mathematics, the manipulation of these formulas, as you're going to see in a second, it gets pretty complicated. I like to think of j 2 pi f as a single variable s. And I write the impedance that way as just being of the capacitors being 1 over s. What I'm going to do is use current divider, voltage divider, all those tools, and then at the end replace s by j 2 pi f. So the impedance of a 1 farad capacitor is 1 over s. The impedance of our 2 ohm resistor is still 2. And the impedance of our 4 Henry inductor is 4s. Okay, so we now want to find V out. Okay, so the complex amplitude V out is pretty clear that this is a parallel combination in series with that impedance. So I use voltage divider, and I find that V out over Vn is equal to 2 in parallel with 4s divided by 2 in parallel with 4s plus 1 over s. Okay, so now we multiply everything out. We get 8s over 2 plus 4s divided by 8s over 2 plus 4s plus 1 over s. Bet you didn't know that electrical engineers have to be very fluent with fractions. This turns out to be one of the things that happens all the time. You can see now why I did not want to write j2 pi f everywhere, because it's complicated enough as it is. This happens all the time, like I said. All right. So we can do some things to simplify this. The first thing is notice that this ratio has some 2's in it we can cancel. I can make that a 4, make that a 1, make that a 2, make that a 4, 1, and a 2. And now we can simplify this. So I'm going to multiply top and bottom by s, okay, to get rid of that. That puts an s squared there, oops, squared, and puts a squared there. And I'm going to multiply top and bottom by 1 plus 2s, which gets rid of it down there and up there, and this becomes 1 plus 2s. Okay, So what we get, I know you can't read that. It's very difficult to read. So let me write it for you. It's 2s squared. I'm sorry, 4s squared divided by 4s squared plus 1 plus 2s. Okay? So this is the name of the game. Use the parallel and series rule. Here we use voltage divider, parallel rules, series rules, and then we simplify. And it really makes your life a whole lot simpler to use S for J2 pi F. So this is what you get, and now I can write it in terms of F, which is what we need to do in order to solve for our sinusoidal source. We need this H of F, and here it is in all of its glory. So S squared is going to be 4 pi minus 4 pi F squared times the 4 gives us a 16, etc. So this is what it is. So at this point, what I would like to do is find the frequency of the source. So the frequency, this has to be written as 2 pi ft. So 2 pi f has to be a half for this example, which means the frequency is 1 over 4 pi. Kind of a strange frequency, but it really simplifies the calculations for this example. I now want to find the value of the transfer function at that frequency. And like I said, this is really makes this assumption of that frequency value really makes the calculations very simple, because the numerator just turns out to be -1. We get that same term here. This becomes j, and the 1 is 1. So we get -1 over j, and the reciprocal of j is -j. So we get j for an answer. So our transfer function at the frequency of the source, that's all we need to know, is what the transfer function is at the frequency of the source, is j, a pure phase shift. So, now we get to figure out what the output is. So, I'm going to think about our sinusoid as being the imaginary part, since it's a sine wave, probably makes it easier, as 10 e to the jt over 2. Well, we know that the output is going to be the imaginary part of 10j e to the jt over 2, where j is that transfer function evaluated at the frequency of the source. And j, again, that's in Cartesian form, convert to polar form, and that's our answer. And I know from the trig identities that that's just cosine. So we stick in 10, and it turns out it's a very special frequency, because what this circuit does at that frequency is convert the sine to a cosine, and it has the same amplitude. That's really pretty surprising, but again, I've chosen a frequency that makes the calculations easy, and that's basically why that happened. In general, as we know, it's going to produce a sine wave at the same frequency with a different phase and a different amplitude. You choose a different frequency, this amplitude will definitely be different than 10. Okay, now I've taught this course for many years, and I've learned what students do that isn't correct. So I want to talk a little bit about what not to do, how to use impedances. So here's the name of the game. We start with a circuit, we know the input, we write it as the imaginary part of something, and we find the transfer function, and we evaluate it at the frequency of the source, and we now know, since I used imaginary part here, that that we use imaginary part here, and that's the correct approach. Okay. Transfer function evaluated at the frequency of the source, we get that from that formula, times the complex amplitude representing the source along with its complex exponential frequency. We take the imaginary part. Well, I have seen students do the following. They just say, well, It's a sinusoidal source. He told me it's just the transfer function times that. Well, that's clearly wrong. At least in this example, we know that the transfer function of that frequency is j. So why in the world would you put in a real valued input and come out with something that's complex valued? This is wrong. You have to think of the source as a complex exponential, and then things go through. So this is not correct. Another thing that isn't very good is to mix the two things together. So you just stick in the source, multiply by the transfer function at the right frequency, and take the imaginary part. Well, that's not what you have to do. There's this intermediate step. Remember, pretending the source is a complex exponential. That's the right formula. This is wrong. Okay, so I hope this helps. We now know a very general result. The output for any sinusoidal input of a circuit is going to be a sinusoid at the same frequency, and the way we find it is by converting to complex exponential form and then multiplying by the transfer function and taking the real or imaginary part depending on how we chose to do. We'll learn more about how to use impedances to figure out what these kind of transfer functions do and to get a much more general, broader picture of circuits.